Okay, let's start. So this will be the 7th lecture for CMSA joint seminar with YMSA in Tsinghua on the literature and history of mathematical science. And I'm glad that Coach Berger will be chair of this session. So let's start. Coach.
Okay, thank you. So before we start the talk, let me say a few words about Professor Shakurov. Professor Vyacheslav Vladimirovich Shakurov, he was born in May 1950 in Moscow, Russia. And then he attended school. He attended also a seminar by Iskovsky, a famous algebraic geometer in Russia, in Moscow. And then he did his undergraduate in Moscow State University. Finally, he did his PhD education under Yuri Manin in the early 70s. Then he started the first job at the Institute of Technical and Scientific Information. After that, he moved to a position at the Yaroslav State Pedagogical University in the 80s up to 1990. Then he spent 1 year at the Institute for Advanced Studies in Princeton. That was 90 to 91. And after that, he moved in 91. He moved to Johns Hopkins University, where he has been a professor ever since. He is also a non-tenure member of the Steklov Mathematical Institute in Moscow. He has had many students, to be precise, 9 PhD students. One of them is myself. And he has done a lot of great work, especially in higher dimensional algebraic geometry, or also known as birational geometry. He proved many fundamental results. He introduced many very interesting, important concepts, and he also proposed many conjectures. So I hope that he will talk about some of these contributions of his in his talk. So let's begin then.
Okay, thank you for introduction, and of course, thank you for invitation. It's a great pleasure for me and honor to talk about this birational geometry on this activity. So, of course, birational geometry, I would like to say a few words. It's very fruitful area and very intensively developed area in the last 50 years. So in 1 hour and half hours, it's 90 minutes. It's difficult to present even the most important results. So I will focus on certain main structures of this subject. So I will work over an algebraically closed field K of characteristic 0. For instance, you can suppose it's complex numbers. Essentially, it's the same. First, I will start from our heritage in birational geometry. When I was studying birational geometry, and there was not too many results as now. And we know basically all birational geometry, all facts. And it was, of course, generators of Cremona group, Max Noether result. And so Cremona group to is group of birational transformation of P2. And the result was that group is generated by automorphism of P2. And another one birational transformation, which is usually called quadratic birational transformation. Then it's here XYZ goes to the inverse. And this in homogeneous coordinates will be the same as quadratic, where the name is coming. Another a more wide area was very well developed by Italian geometrists, but actually they have finished this series. Birational classification of algebraic surfaces due to Casanova, Enriquez, and Severi. That every algebraic surface has a minimal model that is birationally equivalent to a complete non-singular surface S. And this, by definition, such minimal model without -1 curves. This was kind of main construction, but of course, I will not talk about their complete classification or list. I will explain the structures. What is this -1 curve C? This is a non-singular curve, in a non-singular surface, a curve, such that its algebraic curve, and C is isomorphic to P1. So it's projective line, and C square is -1. And the statement was here, and very important for us for today's talk, that if we'll take this -1 curve, then this curve can be contracted on a non-singular surface S prime. So there exists a birational modification. And what means this birational modification? So it's we replace this curve C by its image. It's a point, CSC. It goes to a point. So C image of this curve is a point. And if we subtract this from surface curve C and from surface S prime point, then we have isomorphic open topological these spaces. So it's a kind of modification. So we changed only in this closed subvariety, this model. Of course, here arises one interesting question, how to generalize this. Later we'll discuss. And from point of view of mathematics, this was a correct statement. But this was not a right statement, as we will see later. And so you should distinguish, this is very two different things, to be correct or to be right, especially maybe in politics. And so another important thing for us for today, that these contractions, they terminate. And this is not difficult fact in this situation, because termination here is controlled by Picard number, and Picard number is finite number here. And also what we know in heritage, it's Fano threefolds. It's a result related to Fano. So I will start here from classical definition of Fano. What is this threefold for Fano? So Fano considered threefolds in PG plus 1, so it's projective space of dimension G plus 1, and X is smooth three-dimensional subvariety, such it's curve section. So we take here intersection with two sufficiently general hyperplanes in this projective space. And this result will be in PG minus 1. And this curve section is canonical curve of genus G in H1, H2 general hyperplane sections. So this was the definition of Fano, what means a Fano threefold. And what Fano did, he classified, so it's important for us, their classification due to Fano. And later we'll talk a little bit about this. And also he proved, in certain sense, in Italian style, non-rationality of smooth threefold quartics. So smooth threefold quartics, they correspond to the case when G is equal to 3. So it's a very special case. So essentially he did this Lurie's problem, but his proof, of course, not complete from modern point of view, not so rigorous. He considered some general case, but he didn't consider all cases of his inequality. And also, now I will start to talk about next period. It's also in this period, which was previous to now our birational geometry, there was a new foundation of algebraic geometry. And starting from this new foundation, Grothendieck suggested, and in particular, he suggested to my advisor Manin to start to do this Italian results in modern technique and to reconsider all this result. It was also Shafarevich seminar in Steklov Institute related to this subject. Later was published a book. But for us, for today, it's interesting from this new foundation is a Proch construction. And what does this Proch construction? Its Proch construction states that every projective variety or scheme X over K is isomorphic to Proch of certain graded algebra, but this algebra should be finitely generated. This is very important assumption, finite generatedness of this algebra. And so in particular, how you can use this construction. If you can predict certain properties of this constructed scheme or variety you expect in terms of this algebra, then you need only to prove that your algebra is finitely generated and you will make this construction. So it's very useful. You will see later in birational geometry, this Proch construction. Of course, he did much more, Grothendieck, but we extract from his results what we need here. But there were also non-projective constructions. And they related to birational geometry, but maybe as a kind of sideways. So they go in a different direction, as you will see later. So non-projective constructions appeared in papers of Meshizon and Max Artin, and they appeared as, now we call this Meshizon spaces, and algebraic spaces were introduced by Artin, mini schemes. It's very important objects, and it's interesting that even in this period, Grothendieck introduced the scheme, projective scheme, affine varieties, algebraic varieties, many of these constructions, but already appeared new objects of algebraic geometry that were not in this EGR book of Grothendieck. So it is much larger area of mathematics. And all we see, of course, it's from algebraic point of view, it's not very simple object. And it's not enough, will be maybe 5 lectures to explain what means algebraic space. But to explain what Meshizon space is much easier. So if you consider complex numbers and compact analytical space X, and such that its field of meromorphic functions on X has a maximal possible transcendence degree over C. So what it means is, so it means that maximal transcendence degree is exactly equivalent to dimension. So here we have the result that transcendence degree of meromorphic function is not, meromorphic function field is not higher than dimension on this complex manifold. But when it's maximal, it's called Meshizon varieties. Most of them are far away from projective varieties. And what is the source of this non-projectivity? The source of non-projectivity is related to modifications. So what is the modifications? And you may find very nice paper of Max Artin related to general criterion when modification exists. So it's very useful criterion. So it's, and modification means the following. So we have algebraic variety X, and we have sub variety E in this variety. And suppose we have simple situation. The E is EPM bundle. So it's fibration with very simple fibers. It's locally trivial, and fibers is projective spaces of fixed dimension. And we suppose also that this bundle is negative. So for instance, if this is a point, this is just projective space, and this is projective space has negative, negativity means negative normal bundle. And then we can construct new, but it's usually not algebraic variety anymore. Typically it's algebraic space, such that Z is embedded in this algebraic space. And this, in certain sense, can be constructed functorially and uniquely. And this is one of important construction. But already they understood quite well, these people who constructed, in particular, Meshizon, when they start to construct this variety and started from projective varieties and take this even negativity, then our result may be not projective, especially if we have here these vibrations in these cases. So if we have opposite construction and we have projective variety Y, and we have suppose it's manifold, and we have smooth subvariety and make a blow up, we have opposite picture, and in opposite picture we have projective variety. So in one direction, these constructions, they go to not very good object, much more general object. And of course, it's interesting now we understand much better this object, but nonetheless, our lecture today is more related to projective category, as you will see later. And now one related result, how actually projectivity related to non-projectivity in some cases. This was actually proved first by Piternel, but first I will just state this result. So suppose X is a compact, non-singular Meshizon manifold. So it's Meshizon manifold, non-singular, and without rational curves. We do not have rational curves in this. Then it should be projective. So Peternel asked me this question in late 80s. He proved this for dimension 3. And later, I suggest one conventional proof using minimal model. I'm sorry. Using minimal model program, we can prove that this result in any dimension. And then, of course, certain version of minimal model program were proved by Birkar, Cassini, Haken, and McKernan. And so they also mentioned that their result is enough to establish this result. In particular, this special type of termination they use is enough in this case. And so what is the conclusion from this result? We have the following, and also it has generalization. The same true with good singularities, Kawamata-Lock terminal singularities, and without rational curves. And what is the conclusion from these results? So non-projectivity related to bad singularities or to rational curves. So if you have something where appeared this rational curves or singularities, it may be not projective. It was also noticed by these people like Mishizon, examples like Hironaka of these non-rational threefolds. And finally, I will here should mention what means the rational curve on X in this. And this is one of heroes of today's talk, but maybe not the main. So rational curve in this situation, it's just for over complex numbers, is a mapping from CP1 to X, a non-constant. So it's non-constant mapping. And now I will talk about forerunners. So this person was just before when we start to learn this birational geometry and before we will start this high dimensional birational geometry. Of course, there were some results even from classical Italian geometry in dimension, what I say, 2 plus half, and in dimension 3. And by dimension 2 and plus half, I mean algebraic surfaces over non-closed field of any characteristic. Of course, partially they were also Italian geometry, but they were considered and later developed by Manin, according to this push from Grothendieck, and then Iskovskih involved was in this stuff. And also one result, 1.5 dimension, because it's for result related to relative to dimension of a curve. It's a semi-stable degenerations of K3 surfaces. It's a result of Viktor Kulikov. So it's about smooth minimal with normal crossing, so smooth minimal, this model with normal crossing in the central fiber for K3 surfaces. And he used this non-projective technique. Essentially, he used this, what is called perestroikas. In Russian now it's called flop. I have an example of these flops and of Atiyah type. And he used also some contraction of the divisor. But he worked in smooth category completely, but not projective. And also, it was starting some results and very important results. And was the first kickback, we can say, in this kick to start this birational geometry in dimension 3. It's Leurav's problem. And what means Leurav's problem? So we consider pure transcendental field, Kx1, Xn, of this n variables, pure transcendental field, and subfield. And this subfield is finitely generated over K with transcendence degree n, this maximal possible transcendence degree here, this field. And the question of Leurav is this field is isomorphic to a pure transcendental extension, to this field, even it's embedded. And geometrical interpretation of this fact is the following. So we consider rational dominant map of projective space into X, and a rational field of rational function on X is exactly this field L. That is, X is unirational. And the equation in this geometrical terminology is birational to projective space. Of course, the answer is yes, if n is not higher than 2. N equal to 1 is LeRoth established this result, and n equals 2. It actually follows from Kostanova and Enriquez rationality criterion. This is another important piece from this two-dimensional birational geometry that was developed in Italian geometry. But for dimension n bigger or equal than 3, it's not true, so no. And counterexamples, they are very inspirational for birational geometry and appeared for threefolds for these counterexamples. First of all, this quadric double solid with singularities. And this double solid is birational to a conic bundle with non-connected discriminant. And this was established by Max Hartin and Mumford. So it's later it was developed by many mathematicians. But again, this is not a subject for today, my lecture. And another example was, according to Clements and Griffiths, it's a smooth cubic in P4. So this is, both are Fanas, but this is Fana in a new terminology, Fana in terms of Iskovskih, but not in terms of Fana itself. But this is Fana in terms of Fana varieties. So both of them. And here, Clements and Griffiths, they use theory of intermediate Jacobians. And in a certain sense, they are developed in modern birational geometry in terms of derived categories of this type of object, and some conjectures related to cubic fourfold and Kuznetsov conjectures. And the next example is important, more important for us for today. And this is some smooth quartic threefolds. First of all, some, it means that not all quartic smooth threefolds are known to be unirational, but some of them unirational. It was known even in Italian algebra, some of them unirational. And already Fana uses. But what established Iskovskih and Manin using this, of course, Fana first proof, they actually rigorously proved this using Fana Noetherian inequality in general settings, not as it was proved by Fana in one special, some special but generic cases. And what is in modern terminology is birational rigidity. Later I will say a few words about this birational rigidity. And so any birationally rigid variety is not rational, of course. So this is important for us example. And here is a question even related to this quartic. Is a general quartic unirational? It is rationally connected. And this is related actually in principle to very important problem in modern birational geometry, or we may say unirational geometry. We do not know essentially any example that is rationally connected and at the same time is not unirational. Of course, most of people, they do not believe it's rational unirational, but there are no some instruments still. So it's very challenging problem for a new generation maybe of birational geometries. And so here I will mention some also new results. I mean, this not new results for today, but new results when I started this birational geometry in 60s or 70s. So new results and concepts in higher dimensions appeared. And so here, first of all, I should mention one very technical and important result is resolution of singularities due to Hironaka. And then also Fana manifolds were introduced by Iskovskih. And later it was generalized to Fana varieties. And his definition was very simple, that minus k is ample, is not two hyperplane section canonical curve or something. But of course, when he introduced this concept here, has certain hesitation, maybe it's quite complicated, usually general. And so when he started to his classification of non-singular Fana threefolds with Picard #1, he supposed a condition that in minus canonical linear systems there exist smooth divisors. And fortunately, it was proven soon. And then his classification was working, and he understood from this is the right definition, that my KNS is ample. You don't need additional assumption about structure of anti-canonical linear system. And now we had much more advanced result about anti-canonical linear system for these Fano varieties, even in higher dimensions. And now about these singularities. Already in this time appeared singularities exactly which are needed for higher dimensions, for dimensions even 3 and higher. They are not needed essentially in dimension 2. And they are quite known as canonical for dimension 2. This is canonical at terminal singularities. They were introduced by Miles Reed. And this is also, he did classification of terminal singularities in dimension 3. And in particular, he introduced these compound dual singularities, CDV. And most of important results about threefold singularities, they are still relies on his classification. So it's still very important in dimension 3, his classification. And also, he already used this project construction, and he explained that canonical model, actually, if it exists, it's related to finite generatedness of pluricanonical ring. And if it's finitely generated, this ring, and we can construct this model, we have general type of manifold, what is we say, then this general type of manifold has exactly canonical singularities. But in general, according to modern theory of this adjunction for fibers, if you remove this condition, this general type, and construct proj, again, you will obtain some variety which has some good singularities. It has, in modern terminology, it has singularities of Fano type. And so from this point of view, you see here that both definitions, Fano and Iskovskih, they're actually very related, and there exists one ambient object which includes both of these definition. It's a Fano type of varieties, a Fano type of vibrations, locally or globally, which is more general object of this nature. Okay, and now it's a picture. And this picture about our seminar, which was related, of course, not only to birational geometry, but mainly to birational geometry. And it was usually in a dacha of Fyodor Bogomolov. So it was a kind of summer home. And on this seminar, it was usually quite small, but it, like workshop, we usually have 4 or 5 hours each day for 2 or 3 weeks. And we learn this many modern papers related to birational geometry and the singularities. And here I just mentioned these people here. Maybe most of you know them. This Dolgachev, Igor Dolgachev, Fyodor Bogomolov, Vladimir Sarkisov, me, and Vladimir Danilov, Andrei Turin, and Vasily Iskovskih. So this, and also I should mention, Miles Reed also many times participated in these seminars. There were also some occasional guests, but typically these people was. And now about this breakthrough. So a breakthrough coming from the country of rising sun. This was Mori's theory of minimal model program, MMP, what we say. It's related to Shigefumi Mori. And what we can say in this situation, maybe this is not my phrase, I hear this from many people, maybe from Kawamata. He converted birational geometry into biregular one. So it was a great achievement. But of course, biregular one means that we are working here with projective varieties as opposed to project constructions. And so we move this problem into algebraic settings. This is typically a very important step in any mathematical branches of mathematics when we start to move our theory from general, this maybe not very rigorous statement, into algebraization. So it was a progress in algebraization. So first I will say a few words about what means a model here. Of course, a model of an algebraic variety or of a field L over K. So typically we consider these two types of model, but usually for algebraic variety. Is an algebraic variety Y, and respectively it's either birational to X in this situation, or with the field of rational function L. So we have certain field of rational functions, and we would like to construct this model. Of course, from this result of Hironaka, we know that this algebraic variety of finitely generated field, it has a non-singular model, so we can construct non-singular variety, non-singular model. So it's a good starting point for me. But as we'll see later, that actually it's better to have models with certain type of singularities. And even some people like Danilov were a little bit against this. But at the end, what we have, actually, if even we don't like presence of these singularities, we can describe these singularities in terms of resolution. So finally, we can get some quite coherent picture in this settings. But nonetheless, from my point of view, it's normal. There's some singularities, even as we know in modern log geometry, this is like toric geometry. The toric singularity is considered as non-singular variety. So we can treat certain class of singularities almost as non-singular. And now we'll talk about this main contribution of Mori. It's to have two types of resulting models, or we may say terminal models. So when we start from some non-singular models, then we are starting to transform these models. And as a result of this transformation, we have two types of models. And we should care about these two types of models. So one type of model is a minimal model or minimal variety. And this is not exactly the same as minimal surface, as you will see later in Italian terminology. So it's a new terminology. Projective algebraic, its variety is projective algebraic Q factorial variety X with terminal singularities and Neff canonical divisor. Later I will explain some of this terminology. But one final remark, because I will not focus too much about minimal models. Actually, this is very interesting area of mathematics, because here we have a large spectrum from general type of varieties to varieties of Kadarya dimension 0, where we have Calabi-Yau varieties, very important class for mathematical physics, and somewhere in between. Of course, in dimension 2, we have not too much between. We have like K3 surfaces, abelian surfaces, then we have elliptic vibrations investigated by Kadarya, and then we have algebraic surfaces of general type, where we have geography, which is related to numerical invariants of this general. But here in my talk, I'm more focused on a different type of models. But first I will finish with this definition, because I will use the same assumption for a second type of models. So first of all, what means Q factorial? So it's close to factoriality conditions. We know factoriality condition in algebra, especially for rings, when we have factorial rings. And here Q factoriality means that every wave divisor is Q Cartier. That is some multiple is Cartier. So if we take wave divisor multiplied by a certain number, then it's Cartier. It means it has local equation by some regular function, or in a complex case, it's just by golomorphic function. So it's Q factorial. But Q factoriality in analytical case is quite different from Q factoriality in algebraic case. We should notice also. And then the Neff property. This also independently were introduced. For instance, usually I use in Russian terminology as numerically effective. But this is terminology of Miles Reed, because when he introduced this abbreviation, NEF. He means by this abbreviation not numerically effective, but numerically eventually free. But in modern terminology, of course, many people say numerically effective. And what it means? It means that for any curve on our variety X, its intersection with canonical divisor is bigger or equal than 0 for every curve C on X. I didn't set here, I suppose it canonical divide, most people know. But for this intersection theory, of course, you should know that your canonical divisor is Q Cartier. But because we have Q factorial case, it's Q Cartier, and they have good intersection theory. So we have this condition, it's bigger or equal than 0 intersection for any curve. And terminal, of course, I prefer not to use this resolution to define. Of course, you can find in many books this resolution. I will mention one inductive definition. These singularities of resulting or terminal model, and this terminology is related. So when we have this resulting on terminal models, they have exactly the singularities of terminal type. If we start from non-singular variety and then start a process, later I will explain, to make contractions, flips, then during these procedures, we can get only terminal singularities, nothing else. So these singularities of these models in MMP, starting from non-singular variety, or starting from terminal variety with Q factorial singularity. They are the same, as we'll see later. Of course, there exists analytical definition, but analytical definitions, which I use L2 norm, it's better fitted to Kawamata log terminal singularity or log canonical singularities, to slightly larger class of singularities. And now about Mori fibration. So this is second object. So one of important object for us resulting is minimal model, and another is Mori fibration. And this is was main contribution, of course, in this area of Mori. This is a contraction. So we have a fibration here. Both varieties are normal, X to Z normal variety of projective normal algebraic varieties, such that dimension of X is strictly larger than the dimension of Z. So actually we have a fibration. It's not birational transformation. And X, of course, here is Q factorial, as we explained, with terminal singularities. So singularities for both models are the same, Q factorial terminal. And also this transformation should be elementary. It's the relative Picard number 1 of X over Z is 1. So if you remember, the Siskovsky exactly classified these Fano varieties with Picard number 1. This is exactly the case when this is a point P, and then you have Fano variety, and smooth, for instance, Picard number 1 is exactly this condition. But this condition actually coming from Fano papers. Fano usually called them prime speech, and we try to understand with Siskovsky what means prime speech, and decide finally that it's Picard number 1 may be the best approximation of this. And finally, about anticanonical divisor. Anticanonical divisor is ample always here. So here we have NEF condition, here is ample always. So this is Mori fibration. And examples, of course. So if we consider minimal surfaces, Italian geometry, then they are a mixture of two objects. They include both two-dimensional minimal models, and also they include Mori fibrations, P2 two-point, and also P1 fibration. In this case, Z is a curve, non-singular curve. I didn't say here, I didn't say a word about Z. Actually, Z, it's not very bad variety finally. I will just say here it's Q factorial for Mori fibrations always. And also it has what is we call now this phenotype, locally phenotype singularities. So it's slightly more, in particular, these singularities are rational. So they're quite good singularities. And for Fano-Seyfeld Mori fibrations, I will mention here. Its classification of this Calabi, also this general type is much more complicated here. But even for Fano-Seyfeld, we have three interesting classes. First of all, it's Fana threefolds with Picard number 1. And this in particular includes manifolds, but in addition, we have here about maybe many thousands, even with maybe 1,000 with Picard number 1 with terminal singularities. We know it's finite number, and according to Miles' table, 5,000 all Fanas, but they with different Picard number 1. We do not have a table of Fana threefolds with exactly Picard number 1. It's interesting how to compute them. And then Del Pezza fibrations over a curve. So fibers here is Del Pezza, and Del Pezza surface is example of Fana variety, smooth Fana variety of dimension 2. It's minus canonical class example over point. And finally, it's a conic bundles of the surface. And the theory of conic bundles, of course, was very well developed even before these Mori results. And even it was considered some standard conic bundles. As you will see later, again, standard conic bundles is exactly one of Mori fibrations. So Mori definition fits very well in this birational picture. And now these conjectures I will mention. And these conjectures still open. Every variety X has a minimal model Y or a Mori fibration, where Y is birational to X. So the main part is still widely unknown about minimal models in this case. And the second conjecture that every minimal model has Itaka fibration. So it's so-called abundance conjecture. It contracts exactly the curves with zero intersection with canonical class. And so for general type varieties, it's birational. And for another extreme case, if it's contraction to point, it's exactly what's called Calabi-Yau. But again, Calabi-Yau, it's very specific class for people in math physics. They should have fundamental group trivial. And so it's sometimes very vague terminology. And finally, this Kawamata conjecture, also very important, that S has finitely many minimal models up to isomorphism. So if we consider minimal models, then we have finitely many of them. And first, to finish with these conjectures, I would like to say they are very important and they are crucial for birational geometry. And this is also usually a good sign for any theory, that any theory is still alive if it has such powerful conjectures. So birational geometry is still very alive. It's not ready to go to archives. And here we have very interesting example related to Kawamata, this case. So this actually conjecture related to periods, as I understand it, Hodge structures. And the statement here, the following, that if we consider K3 surfaces S, then every K3 surface has finitely many models S prime with dual singularities and with this birational contraction. And actually you can replace this, I will say a few words later about these contractions, that this is K3 surfaces with dual singularities. So if you have such surfaces, which are non-singular, they may have high Picard number, up to 19, and you have a lot of -2 curves. So when you contract this -2 curve, quite arbitrary, you can expect that maybe you will construct many different singular models. Not, you have only finitely models up to isomorphism. And the result is related to Torelli's theorem for K3 surfaces, why I mentioned here. So Nikulin explained this result, but he used a result of Petetsky, Shapiro, and Shafarevich, which is related to Torelli's theorem for K3 surfaces. So this means that there are no other proofs, I do not know, only using periods and this Hodge structure of the surfaces. It's a problem maybe more from we can say Hodge theory of modules than the theory of birational geometry. But it may be quite involved in modern birational geometry, very involved in many problems. Okay, and now I will say, of course, I should say about how works this program. So we know now this, our terminal or resulting models minimal models and Mori fibrations, and how to get these models. So here, another very important thing that was introduced by Mori, this extremal rays and extremal contractions. I prefer to talk here today about extremal contraction, not seriously mention this extremal rays. But this can be explained in the form of divisor in modern technique. So let X be a projective Q factorial variety with terminal singularities. For instance, non-singular. This is important for us. Or it's variety which was constructed during our process when it's appeared terminal singularities. First, I would like to stress here this condition, this projectivity we use always in Q factoriality and terminal singularity. And projectivity is the core of Mori theory. So Mori theory is very projective. And so, for instance, this is one of problems how to organize, to generalize analog of Mori theory for Köhler manifolds. It's one of these problems we should look at slightly a very different category. It should be different ideas here. So this is a first step here. So if minus, oh, here's a, of course, misprint. If Kx is Neff, it's quite possible. If Kx is Neff, then X is minimal model problem, not minus Kx. It's minimal model. Otherwise, there exists an extremal contraction. So extremal contraction exists when we have some curve which has negative intersection with canonical divisor. And there exist certain results of course, Mori, very important, how to deform this curve and to construct some extremal curve in this direction. But there exists also modern approach, how to construct first contractions and then to construct this curve after that. And so this, I put a check here. So if minus Kx is Neff and X is minimal, everything is fine. Otherwise, this is our step in our algorithm. There exists an extremal contraction with projective variety Y again. So we're working in projective category, and such that the relative Picard number of X over Y is 1. Again, we have this elementary property, which actually coming maybe from papers of already from Fana papers. And minus Kx is ample over Y. So it's, in certain sense, it looks like Mori fibration, but not, as we'll see later. So if dimension of X strictly larger than dimension of Y, then X to Y is a Mori fibration. Again, I put here a check, the check. So we are done in this situation, and we have these two resulting models. But what to do in otherwise? So otherwise, Y is projective and birational to X. So we have birational contraction. We have birational variety. In other words, Y is a projective model of X. But this model may be not quite good. It may not have this good singularities, terminal or Q factorial. And here we divide these singularities in good or not good. So if additionally X to Y is a divisorial contraction, that is, the exceptional locus of contraction contains a divisor, then Y is projective Q factorial with terminal singularities. So this is a good case. And P is a prime weight divisor in this case. And the entire exceptional locus is exactly this prime weight divisor. And the Picard number of Y is the Picard number of X minus 1. So we have a decreasing Picard number. So if we would have just only divisorial contractions, then we are done. After finally many steps, we have this contraction. Of course, if we are working in dimension 2, we always have divisorial contraction, because we should have exceptional locus. It should be not finitely many points. So dimension 2 is fine. But in dimension 3, if we have divisorial contraction, it contracts a surface. But it may contract the curves. If it contracts curves, it's a small contraction of this unit. And so in this divisorial case, we replace our varieties as in a program, in a software, x by y, and return to the start. So to return to this starting point, it's projective Q factorial variety, but now maybe single with terminal singularities and go further. Again, otherwise, if it's not good variety and this contraction is small birational, so small birational means its exceptional locus has codimension bigger or equal than 2 in X. And Y is projective and birational to X, but Y is not Q factorial in this case. Certainly, and because it's not Q factorial, we can define that is terminal or KLT. So it's chi Y is not Q Cartier. Moreover, if it would be still Q Cartier, we can try to use this condition, but it's not Q Cartier. We don't know, it's NEF or not NEF device. Y is not terminal. However, all even non-Q factorial the singularities of Y have phenotype, as I mentioned. So it's possible to introduce here phenotype of Y. This is good singularities. And now we will talk about flip, or in Russian it's called perestroika. Its terminology came from Kulikov, much earlier before Gorbachev, our leader in Russia. And now in Russia it may have some negative connotation, and some people in Russia, they prefer even to use this word flip. Even I still prefer to stick this old word perestroika. It sounds in Russia quite well. And so suppose that we have this small contraction. This contraction is also called flipping contraction because it's related to flips. And the flip means the following construction. So exists a small blow up X plus of my variety, and this blow up is in the commutative diagram of this, where X plus is a projective Q factorial with terminal singularities. And so actually, this is exactly what means regularization of birational geometry. We construct this contraction, and then we construct blow up. But we need to explain how to do this blow up. And what's the problem here with this blow up? But first I will say, if we have such constructions, that's X plus is a small blow up, so it's small contraction here, Q factorial with terminal singularities, then it has the same Picard number. X plus has the same Picard number. And with the following properties, the relative Picard number of X plus over Y is 1, and Kx plus 1, canonical class here, is ample over Y. So canonical class here is negative anti-ample, and here is ample. So we have this flip here, twist in intersections here. And Y has only two actually projective small blow-ups, Y over X. So if we consider this variety Y locally in algebraic category, there exists only two small blow-ups, which eliminate this non-Q factorial property. And these two small blow-ups exactly flipping contraction and results of a flip. And they can be constructed as a Proj. So we use this Proj construction, as I mentioned, from this EGR of Grothendieck, and of local pluri-anticanonical ring. So in this situation, it's pluri-anticanonical ring and pluri-canonical ring in this situation. So we respectively have two algebras, local algebras, related to pluri-canonical or anticanonical ring. And essentially, they are related to not Q factorial property of K. And this small blow-up removes this. So it resolves this problem with Q factoriality. It makes canonical class Q factorial, but either way, either it makes it positive or negative when you make. This construction is known now. Mori started from geometrical setting of this construction and reduced to this to semi-stable degenerations construction. Also, my starting point of view was reducing to semi-stable degenerations to relative this category construction. And it's threefold log flips and more general. And then I explained it in another paper, PLT paper, related to PL flips, how to do this in terms of this finite generatedness of certain algebra. And later, this finitely generatedness, it was used in all of this construction. According to Hsu and Birkar, Cassini, Hayek, and McKernan, this flip was finally constructed. And from my point of view, the most right construction here, they are correct, but the most right construction, of course, in this case, is a result of Hayek and McKernan, that if we have termination of our program in dimension n-1, then we have flip in dimension n. This is very conceptual proof, and not so technical. In this case, we put x equal to x plus and return to the start. And actually, we are finished modulo this conjecture about termination. So we have these flips. And if the process and the flip terminate, we get a resultant model, minimal model or Mori fibration. And here we have conjecture about termination. After finitely many flips, we get a minimal model or a Mori fibration. And now one example, this Mori category of projective varieties, projective construction versus Kulikov, Viktor Kulikov construction. So let's x over t be a projective semi-stable degeneration of surfaces, maybe not K3, more general type, over a curve, or over discrete valuation ring. Then we can apply relative minimal model program to x over t. I didn't say a word just now about this, but it's similar to absolute minimal model program that we considered earlier. And so it's the same type of result. And resulting models are relative minimal models y over t or relative Mori fibration y over zt. So we have two types of resulting model. Type of resulting model directly related to the type of general fiber. If general fiber, for instance, has minimal model, then the special fiber also has minimal model. It's general fiber has Mori fibration, that Mori fibration has special fiber. But of course, it's not Mori fibration in usual sense. It's a kind of log version. Singularities of y of any model in this minimal model program are very special. They are not only terminal, they are semi-stable, because originally we have semi-stable degeneration. And again, you can ask how to define. There exists abstract definition of these singularities, and it was introduced by Corti, for instance, abstract. But in my paper, when I introduce the semi-stable terminal singularity, I use induction. So this concept, if we have semi-stable degenerations, all singularities which we can construct during this process is semi-stable terminal singularities. For instance, what we know that every semi-stable terminal singularity of index 1, so it means it's locally canonical divisor is Cartier divisor near the singularity. They has a small projective resolution, not projective resolution. So this resolution exists in analytic category. If we have small analytical neighborhood, it became not Q factorial. It has this resolution in this mesh zone algebraic space. And this holds for index 1. For index 2 and 3, there exists description. In my paper, it's described for any indexes, these singularities. Thus, if the general fiber is a K3 surface, then a resulting model is a minimal model of index 1. And its small resolution is exactly a Kulikov model for degeneration with additional restrictions. Additional restriction, we have this Gromov-Witten numbers, we can say. It's how many rational curves. Of course, in this resolution, we have rational curves when we go from projective variety to non-projective. And the number of rational curves is bounded here because we have case resurfaced degenerations. In general, again, it's not bounded for index. It's Gromov-Witten. How many rational curves? It's not higher than 19. It was also known for Kulikov. And this was also investigated partially by Kulikov. But in modern mathematics, you can find even in new developments in papers of Alexeyev in degenerations of case resurfaces. Oh, here I have one mistake. It should be X over T. I had no time to correct this file. Maybe some other typos. And so similar results holds for semi-stable degeneration of surfaces with a numerically trivial canonical divisor, Calabi-Yau surfaces. For instance, degenerations of Enriquez surfaces, they have index 2, because Enriquez surface has index 2. Double Cava has canonical divisor with linear equivalent to 0. But Enriquez surface has its index 2. This index of this canonical divisor is related to this index in the case when it's numerically trivial for degenerations. And this is exactly related to examples of Crowder and Morrison, actually counterexamples to results of Kulikov. He stated in his original paper, not only smooth case, but also degenerations on the Enriquez. And of course, it's not true for Enriquez, but for Enriquez, it has special singularities. And in this paper, my paper, it's explained what singularities we have. And now about minimal models. I will say a few words. If X has a minimal model Y, then any other resulting model Y prime is also minimal model. And the birational transformation from Y to Y prime is a crepant or a flop. So it essentially preserves type of singularity and numeral intersection. It's possible to define this, all intersections with curves are preserved for crepant transformation. But we have much more conditions here about singularities. And actually both conditions are equivalent. If singularities, they preserve what is called discrepancies, it's the same as to preserve numerical property, crepant. As I told you before, this theory of Iskovskih, like Fana, is related to theory of singularities like introduced by Miles Reed. So it's kind of general philosophy. But what is interesting here, that any such crepant transformation can be factorized into elementary flops. So we have these elementary flops. And so what is elementary flop? And here we have two small birational contractions, and relative Picard number is 1. It's like for flip. But difference with flip, that both canonical divisors are numerically trivial over Y1. So we have here slightly different divisor. Again, we have two blow-ups here of this divisor, but it's related to polarization divisors or anti-polarization on this flop. In three-dimensional case, it was maybe first time intensively investigated by Kohler, these flops, and in his paper about threefold flops. And conjecture, it's finite generatedness, as I state this conjecture. The generalization of Kawamata conjecture, that the groupoid of minimal models, so if you consider groupoid of all minimal models of X, X is fixed, is generated by a finite set of elementary flops, like these flops, and isomorphism. So we can make isomorphism with different models. So it's a kind of version of this Max Noether result, but for minimal models and their finite generatedness. But of course, the difficult part is Kawamata conjecture. If we know Kawamata conjecture, it's easy to derive from this. And we have here much more general result that actually we can enchant this category and we can add zero contraction, what is usually called like elliptic or these fibrations or case resurface or Calabi-Yau fibrations. They also finitely many of these objects. And now it's a picture relevant to this talk, what we talk now. This is when I was very young, and it was 1964, and we have been in summer camp. It's a different seminar, but not in mathematics. It's more related to sport activities and relaxing for summer for schoolboys. And here in this picture is Sarkisov. He is Sarkisov, and he is me. So we're here on this picture. It was 1964. And now I will talk about Mori fibrations. And what is comparable theory like flops or something? So in this elementary transformation of flops, if X has a Mori vibration, then any other resultant model is also a Mori vibration. And here we have very complicated actually picture. For general types, in most cases, we have a few models. But for most of rational varieties, especially, for instance, even for non-rational varieties, for Fano varieties, we have a lot of Fano models and different type Mori vibrations. And so here I will state Wick-Sarkisov problem. And first explanation of this problem, conditional. And first of all, in degenerate case was in our survey with Iskovsky. And later it was using Birkar-Heiken, Cassini, McKernan, Heiken, Cassini paper, and also they restore this picture. And in our paper with Choi also, this Wick theory. So what means this birational transformation? So it's the birational transformation. What means this Wick-Sarkisov problem? It means this birational transformation from one Sarkisov model, y prime, z prime, from y to z, can be transformed into elementary transformation. So it's similar to elementary flops of Mori models or Sarkisov links. So we have here elementary transformation, where each of these vibration is a Mori vibration, each of these objects here. And every transformation, y1 to 2, y2, and so on, are Sarkisov links, or in his original terminology of Sarkisov, elementary transformation of Mori vibrations. So every Sarkisov link has a center. This I use from Choi paper. So it has a center, y over t. And it can be explained as a Mori vibration. So it's a contraction with y birational to x of projective algebraic varieties, normal projective varieties, such that dimension of y is strictly largest dimension of t. Y has terminal singularities. But here, you see, we do not have condition, q factorial or terminal. We have just terminal singularities. And relative class number, if we consider here, not Picard number, relative class number is 2. And minus canonical class is ample over t. So this is a center. And the statement, if you have Sarkisov link, it has a unique center. And if you have center, you have a unique Sarkisov link. It's depend on direction, only in one or opposite direction. And now how to do this? So if additionally y is q factorial, for instance, I will explain in this situation, then y over t has the relative Picard number 2. And the relative minimal model problem gives, as a result, models to two vibrations. So we go in one direction and second, because we have here, usually it calls two-ray game. And so it's automatically you have two constructions, y1 to z1, y2 to z2, just using minimal model program. And there are two Sarkisov links, one goes to y1, another to y2. Two Sarkisov links. And so this is a picture. So here this is central. Sorry. So here's our central object, it's in center. And here we have this construction, minimal model program. Actually, it can be constructed into a movable divisor, movable part. And here we have Mori vibrations over this base 2. This is the base of this Sarkisov link. And y, if y is not q factorial, we should make before a q factorization into a Wick center. We have two q factorization, as we know it's according to this like relative elementary flop. And then we have these two programs again. So it can be constructed. And in particular, these centers allows us to introduce moduli for Sarkisov links as for Mori vibrations, because moduli, they are related to the moduli of central objects. So usual Sarkisov program has a quadruple. So what is the difference between Wick Sarkisov problem and usual Sarkisov? So usual Sarkisov program has a quadruple of invariants. Here again, I'm missing here, yes, invariants. And termination of this invariant, quadruple invariant. And termination of this invariant is still unknown in dimension bigger than 4. In dimension 3, termination of this invariant was established by Corti, and he used one special thing. But of course, it's related to ACC for not log canonical threshold, but for canonical threshold. So this is the main problem which exists here, termination. But Sarkisov theory with these quadruples and strong Sarkisov theory, it's much stronger. There exist some results in birational geometry that you can prove using strong Sarkisov theorem, but not weak Sarkisov theory. And there exists also generalization of this. I told about this in the conference of Mori in 1911 as elementary relations. They are related to center of class 3 for higher syzygies or higher syzygies. In this, we have a contraction y to t with y is birational to x of projective algebraic varieties, such that, again, dimension of y larger than t, y has terminal singularities. It's always the same as for Mori fibration or center for Sarkisov ring, and the relative class number of y is 3 now. And then you can respectively consider 4 and high on. So you can consider all spectrum. And minus chi y over t, the anticanonical class is ample. And what is stated here? As I construct this Sarkisov link, every relation between Sarkisov links can be given in terms of elementary ones. And elementary ones can be given by similar picture. You construct all Mori models, you will construct some Mori fibration, smaller ranks. So you can construct smaller ranks. There exists an alternative modern construction, which is maybe a little bit involved. And at a certain point, it's not quite consistent because it uses one condition, which is not consistent with general theory of minimal models. And by Blank, Zimmerman, and you can find in their paper. In terms of what is called fibration of rank 3, for instance, you consider that. You can reconstruct this fibration from this picture. Again, you can consider module of these papers. And here's a very interesting equation which is related to finiteness certain. But here expected many finitenesses, but we don't know still some conditions of these finitenesses. But at least the first question for me, which pops up, is the following. Suppose that Z is a Mori fibration. And we consider Z base of a Mori fibration, or more generally center of syzygies T. Is the problem, are they bounded or as not biregular, but even finite in birational category as birational varieties? Of course, for rational varieties, it's not a problem. It looks like not a problem in small dimension. It's related to unirationality because you consider image of rational varieties. Rational, maybe not rational. But for curves, we know. And it's bounded birationally or not, this. Birationally, this center. And now about generic fiber. If you consider generic fiber of any center, it's a Fano variety with terminal singularities. And this boundness already is known. Its finiteness of them is known. It's very important result, and I think it will have many further implications in birational geometry. It's a result of, I usually call this BBAB. It's Birkar proof of Borisov, Alexeyev, and another Borisov conjectures, two brothers of Borisov. As it's Fano varieties with terminal singularities of bounded dimension form a bound family. I just consider here very small version, baby version of this result. We can say baby BBAB. And there exists much more general results here. We need to explain what means epsilon log terminal, what is Fano type. So you need to put this. And now I will say about rigidity. I mentioned before this already. Fano was interested in rigidity. And a Mori fibration is rigid, I like to say, but like Pukhlikov and some people like to say very rigid if X has only one Mori fibration generically over the base. So it means that we consider this fibration over the base, it means over functional field. And so it's from Grothendieck point of view, it's over this point. If it's such unique, then we have rigidity. For instance, if the base is a point, then rigidity means this Y is Fana with terminal singularity with Picard number 1, and this is the only Mori model for this variety, like Quartic example. This is, I mentioned this example. Iskovskih and Manin, every smooth threefold quartic is rigid. Another important example is according to Sarkisov. And it's related to Sarkisov theory, but actually to prove this result, it's not weak Sarkisov theory. And there exist modern, very short proofs. But they use, of course, these developments in weak Sarkisov theory. So let X to Z be a three-dimensional standard conic bundle. And what means standard conic bundle? It's possible to explain in terms of Mori fibration. Equivalently, X to Z is a Mori fibration over a surface with non-singular three-dimensional X. So actually, non-singularity of surface follows from non-singularity of X if it's a Mori fibration. So, and then it's a standard fibration. So if the standard fibration such that 4kx plus c is not empty, this linear system, where c is degeneration of this conic bundle. So it's a curve over which our fibration has splitting fibers. They are not P1, the union of two P1, bouquet of P1. Then in this case, X over S is rigid. Any other Mori fibration is a conic bundle over T, and generically over the base isomorphic to the same conic bundle. So essentially they have birationally the same conic bundle structure. And so weak Sarkisov theory very well works for the result of this type. But of course we need, to prove, for instance, in modern proof of Mori of result of Iskovskih Manin, we need Max neutral inequality, and the best modern proof of Max neutral inequality is the Corti proof, and also there exists some result of Pukhlikov, more general, and Chiltsov result. It's some generalization of this. They use sometimes slightly different techniques of hypertangency, more classical Italian technique. And so MMP also, this is a tool to investigate algebraic geometry, and it has natural generalization. A log minimal model program, LMMP. Here I will very briefly mention this. Pairs should be replaced by projective varieties with boundary. So pairs should replace projective varieties. And these boundaries are some of weight divisors with boundary coefficients, so division coefficients between 0 and 1. So it's a boundary divisor. And log terminal, LT for short, and log canonical singularity should replace terminal and canonical singularity. So we have no new class of singularities. Also useful some other singularities, Kawamata log terminal singularity KLT, divisorial log terminal singularity, and pure log terminal. So we have a huge spectrum of singularities and very interesting type. And here we have Neff condition should be replaced by Neffness of canonical class plus boundary, and ample condition by anti-canonical class. It should be replaced by ample condition by minus canonical class plus B. And so we have respectively log minimal model program, log Fana varieties, etc. They replace minimal models, Fana fibrations, and so on. So we have this thing. Log minimal program also is important in dimensional induction, in the proof of construction of flip and for termination. So we need this log minimal model even now. And the latter can be shown in terms of geography of log models. And now I'll explain a little bit geography of log models. So suppose that we have divisors, finitely many weight divisors, prime weight divisor E1L, on non-singular projective varieties for simplicity, under generality condition. So what means generality condition, I will explain. So we have a cube, 0, 1, L of size and multiplied by itself many times. Contains a closed convex polyhedral cone with points, BJs. The points are coordinates of our boundary that we will see later. Corresponding log minimal model will be XB. So it corresponds to a point in this pube. Has a log minimal model YBY exactly for B having these coefficients. So we replace, because fixed divisor, we consider this a vector, this divisor in this space. And what we know about this, that this N is a union of finitely many convex rational polyhedrons, Ci. And so itself, it's also convex rational polyhedron. And these polyhedrons I call countries, some people they call chambers. And this chambers corresponds to different models. If we have generality condition, then all internal points of this model, of this cube in these countries, have only minimal models, YBY, with the same Y. So for all these models, we change only BY, but Y is the same for these minimal models. We have generality condition. And they are log canonical. So KY plus BY is ample. So it's a perfect model in certain sense. But when we go to boundaries of these countries, to facets, then we have two types of facets, flopping and divisorial facets. Between two countries, Ci, Cj, which has general type, all internal points have two minimal models related by an elementary flop. As I explained before, we have two elementary flop or elementary flip is related to this construction. Or an elementary divisorial contraction also should be added in this picture. And contraction numerically trivial with respect to Y plus BY. And these models are coming from neighboring countries, I, A, J, this model. Of course, it may be other models, but this coming from countries. And another is Mori fibering facets. On the border of this polyhedron, inside of this cube, but not between countries. So it's with negative part where it's outside of this domain. All internal points of such a facet have a unique log minimal model YBY. They have a unique log minimal model which is coming from one of neighboring countries, Ci. So it's, and with a fibered log Itaka contraction. So we have here YBY, this is log Itaka fibration. And the contraction, if we forget here about boundary, then contraction exactly here is a Mori fibration. So you have here two types of facet. One facet gives us this flopping, elementary flopping, and another facet gives you this Mori fibration. But what is about elementary transformation, Sarkisov links? They also fits to this picture. Sarkisov links connects Mori fibering facets. Links corresponds to ridges. So you have two facets. So this is like sides of some mountain, and it has some ridge. And on a ridge, we have exactly this link between these facets. So this was first explained in our survey with Iskovsky, as I mentioned before. In the case when you have just two divisors. Of course, if you have two divisors, it's very rare that you have generic case, that you have such nice picture. And two divisors, they are quite natural. I take one Mori model. On one model, I take some polarization, good polarization, another model polarization. And then I consider this, comparing these two polarization of divisors. And I can make polarization take like a prime divisor using Bertini results and so on. But actually, it doesn't matter. It was stated also that minimal model program, minimal model program, the general case can be easily done by perturbation. So, but perturbation here is quite special. Perturbation here means that from the general picture, what we can do, we can add a lot of divisors to our devices. Then we have general case. And then we need to change our coefficients, because here we have only coefficients with restrictions. They are zero for other new divisors. But after perturbation, they have small coefficient for new divisors. And after perturbation, you get this picture. And Heiken and McKernan, they, of course, use this very powerful tool. And it's powerful tool from their paper with Birkar and Cassini is working here, fortunately, because it's still all termination problem. It's not solvent, but here it's enough termination with scaling. And then they remove this log minimal model program assumption. And so it works. This picture works in any case. So we have not only this Sarkisov weak problem, but we have much larger picture. And perturbation also was established by my students, Choi, and we wrote later our joint paper. We put some of his results, my results on this subject. Okay, so I'm finished on this. Stay safe and healthy. It seems to be even 2 or 3 minutes earlier.
Okay. Any question? There seems to be one. There seems to be one question. I'll read it. It says that, as you mentioned, birational geometry can go beyond projective category. How then is the motivic invariance like Hatch structure or period related to birational geometry?
Or this equation, not to me. There exists actually some expert in this. Of course, it's more related to derived category and all this motivic theory. It's quite important and developed by Chinkel and Kontsevich with rationality type of results. So it's I mentioned three main instruments, but actually there exists fourth one, bicolor related to generations, how to prove like Lorentz type of problem. But each of this direction, it's also flourish. It has a lot of generalities. And definitely Hodge series should be related. We know certain finiteness like Kawamata type. Fortunately for like Birkar type results, or for results of Borisov type conjecture, when we have phenotype varieties, then we have bounded moduli. We essentially working with very good type of moduli and this log category of this log module. But when we consider even usual Calabi-Yau, it's much more difficult question. And here one question related to this finiteness, it's conjecture by Fujina and maybe Mori also, that if we fixed this Calabi-Yau, I mean numerically trivial canonical divisor in any dimension n, it implies it's some multiple is linear equivalent to 0. So it's, but what multiple? And is it multiple bounded? And the answer is positive if we know that there exists disintegration of these varieties. It's some resolution such that middle homology group of this variety is has bounded dimension. Of course, it's related maybe not to Hodge theory, to topology, but nonetheless, this topology is related to Hodge theory. Okay, this is the answer. It's very vague.
Okay, thank you. Any other question? Okay, for the moment, I don't see any questions, but maybe I ask you something very general. Do you have any advice for young people, probably on this list now, there may be a lot of young people listening here. Do you have any advice for those who want to work in this field or those who already work in this field?
Of course, here my advice is the following. Of course, this what I mentioned, this example of Nikulin of case resources, it's interesting to develop, and we don't know. Of course, here there exists some stronger conjectures of Yau about boundness of, I believe, maybe not all Calabi-Yau threefold, but maybe certain classes we should understand. But nonetheless, it's optional, for instance, with trivial fundamental group. So it's a good starting point for many this undergraduate student when I started their career. Like for instance, for Birkar when he started from complements in dimension 2 or something, trying to solve this problem. Maybe it will have later higher generalization, higher dimensional generalization. So even still dimension 2, it's very important. And of course, maybe it's more analytical type of problem, but there exists maybe more type of birational related problem to algebraic geometry. It's about this termination I do not insist to investigate ACC of analysis. Maybe there exists some other approach how to get this termination. It's difficult to say. It's worthwhile to do and to start to do in dimensions, again, small. And there exists, I mentioned this conjectures about unirationality. It needs some new invariants, but it's a difficult type of problem, any of them. Of these problems, it's related and about some control of singularities, like mentioned here. If you have standard Mori fibration, it's enough non-singular above, then non-singular beyond. There exists generalization of this conjecture by Mike Kiernan and me, and some people working on this. Also, it's related to this general structure of singularities and this birational picture. And we need this result for practice.
Okay.
But in general, I wish him a luck to have some new ideas like Mori. They can turn down all this world of birational geometry, because in classical geometry, we contract with condition. It should be negative divisor, my CK. Why people to use this normal negative condition? But Mori stated that it's a secondary thing. The main condition should be negative with respect to anti-canonical device. This is the main condition.
Okay, thank you. Is there any other question? There seems to be one question. It says, are there any books? Let me read the question. It says that, is there any new books for
I see how I can read also.
Yeah, I see. You can
Mentioned birational came beyond projective. It's
no,
another question.
There is another. I think he is or she is asking about maybe books or some texts for people who want to start this field.
Of course, we have now, we can say, more classical books like Kohler and Mori book about high-dimensional birational geometry. But also there exists Matsuki book related to introduction to Mori series. But actually, we do not have too much, unfortunately. And this is understandable because still we do not have, in certain sense, right point of view, even in three-dimensional case, for many results. But what is related to Haydn? But nonetheless, it exists a lot of papers very important to this subject. And for instance, a very classical paper of Kawamata Matsuki Matsuda, and also papers. There exists, of course, beautiful books of Kohler is related to resolution of singularities, but not to birational geometry, and also to singularities is minimal model program. So exists certain literature, and also some conference papers related to do this type of results. So about singularities exists nice expository papers of Miles Reed, so it exists very nice literature in total. So maybe if it finally will be prepared in a print, this my survey introduction, of course I will add extensively this literature. But it's better to have more precise question. But again, it takes some time to correct these results, and it's to find more right proof, more conceptual proof. It takes some, even to find, like Corti find a new proof of Noether-Fana inequality. You can open this proof. It gives you an example. Even we have already proven results, like Bricard result finite, something. It's to find some new, maybe, kind of approach to this, on some non-vanishing form, anti-canonical class, wondering to find the best in this case. It's difficult to say. But it seems to me some of them quite optional, like this Bricard proof, but close to option. But some of them, they need this kind of polishing.
Okay, thank you. So yeah, the answer was that there are many texts, some books by Kohler, Mori, by Matsuki, and so on. There is also a lecture note on my website.
Oh, yeah, maybe some lecture notes.
Yes, it covers some very basics of the theory, and not every aspect. But as this is available for free, you can just download it from my website. Okay, there seems to be another question.
Yes, a question about why link. It's very strange because when Sarkisov introduced this terminology, he say that this is elementary transformation. Elementary transformation. Yes. But Miles Reed, it seems to introduce this term link. So it's a question to Miles Reed. But a link, it means something which join together two things. You see this diagram. It's not related to topological links. It's even something related to topology. Again, you can find color paper is about real geometry. We consider real geometry. Then for threefolds, flops, we consider flips. So you have real curves. Then transformation near these real curves is well-known surgery, but we know in topology of three-dimensional variety. So there exists certain relation to topology of flips and flops. It needs some more developments. And even there exists a relation between a proof of Poincare conjecture by Perelman, yes. It's related to like geography. So he uses flow. And what we do modern proves this. Birkar, Cassini, Heiken, and McKernan, they also consider this like big cube with models. And if we add very big divisor, we have log model. And then we change this coefficient and move along these models. And when we move these models, it's the same as a flow for this matrix, Kellenstein matrix, or sum of metrics we can use. So this is a flow. And so maybe it's finally, we need a kind of Grothendieck who will find this general picture for all these flows and all this geometry.
Okay, thank you. Is there any other question? I don't see any question. So maybe if there is nothing else, maybe let's thank Professor Shakurov. And I hand it back to Professor Yao.
Well, thank you very much indeed, Professor Sakharov. And well, we are very successful to have these lectures, and we are looking forward to listen to Professor Birkar. So
Okay.
thank you very much.
Thank you for the invitation.
Yeah, thank you.
Thank you for Birkar.
Good. So I hope you write up your lectures. We are going to publish it.
Yeah, I hope it takes some time, sometimes a year or two.
Okay, thank you very much.
Okay. Bye. Thank you.
Bye.